The telegram arrived at the Kaiser Wilhelm Institute in Berlin on a cold December morning in 1938, and its contents would change human history in ways that the sender, chemist Otto Hahn, could not possibly have imagined when he sat down to compose the message to his former colleague, Lise Meitner. Hahn and his research partner Fritz Strassmann had been conducting experiments bombarding uranium with neutrons, expecting to create heavier elements through neutron capture, as previous experiments had suggested. Instead, their careful chemical analysis revealed something impossible according to all existing nuclear physics theory. The uranium atoms were splitting into lighter elements, specifically barium, releasing enormous amounts of energy in the process that Hahn's measurements could detect but couldn't explain. Meitner, an Austrian Jewish physicist who had fled Nazi Germany just months earlier and was now living in exile in Sweden, read Hahn's telegram with immediate comprehension of what the experimental results meant, even though Hahn himself seemed uncertain about the implications. She discussed the findings with her nephew Otto Frisch, also a refugee physicist, during a walk through snowy woods near Kungälv on Christmas Eve 1938. Together, they worked through the theoretical calculations that explained what was happening. The uranium nucleus was splitting into two roughly equal fragments, a process Meitner termed fission, by analogy with biological cell division. The energy release came from the small amount of mass that disappeared during the split, converted to energy according to Einstein's famous equation relating mass and energy. The calculations showed that each uranium fission released approximately 200 million electron volts of energy, an almost incomprehensible amount from a single atomic nucleus. More significantly, Meitner and Frisch realized that the fission process likely released additional neutrons that could potentially trigger fission in other uranium atoms, creating a self-sustaining chain reaction. If such a chain reaction could be controlled, it would provide an essentially unlimited energy source. If it couldn't be controlled, the energy would be released all at once in an explosion of unimaginable power. A few pounds of uranium undergoing complete fission would release explosive force equivalent to thousands of tons of conventional explosives, creating a weapon unlike anything that had ever existed. News of the uranium fission discovery spread rapidly through the international physics community during early 1939, as Hahn published his experimental results, and Meitner and Frisch published the theoretical explanation. Physicists in laboratories across Europe and America immediately began conducting their own experiments to verify and extend the findings. Enrico Fermi at Columbia University in New York, Frédéric Joliot-Curie in Paris, and numerous other researchers quickly confirmed that uranium fission was real, that it released tremendous energy, and that it produced additional neutrons that could theoretically sustain a chain reaction. Within months of the initial discovery, the basic scientific principles that would eventually enable both nuclear power and nuclear weapons were understood by physicists worldwide. The outbreak of war in Europe in September 1939 transformed uranium fission from an interesting scientific discovery into a potential military technology of terrifying significance. German occupation of Czechoslovakia in March 1939 had given Germany control of the richest uranium mines in Europe, located in Joachimsthal. The German army had immediately restricted uranium sales and begun stockpiling the material, actions that suggested German military authorities understood the potential military applications of nuclear fission. Refugee physicists who had fled Nazi Germany, particularly Leo Szilard and Eugene Wigner, became increasingly alarmed that Germany might develop atomic weapons before the Western democracies even began serious research programs. Sillard and Wigner understood that convincing the United States government to invest in atomic weapons research would require an intervention by someone with sufficient prestige and credibility that political leaders would take the warning seriously. They drafted a letter explaining the potential for atomic weapons and the danger of Germany achieving a breakthrough first, then approached Albert Einstein, the most famous scientist in the world, to sign the letter and lend his enormous prestige to their warning. Einstein, a committed pacifist who had previously opposed military applications of science, wrestled with the moral implications, but ultimately agreed that the danger of Nazi Germany possessing atomic weapons was so grave that warning the American government was necessary despite his personal opposition to weapons development. The Einstein letter reached President Franklin Roosevelt in October 1939, forwarded through Roosevelt's informal advisor, Alexander Sachs, who explained the scientific concepts and strategic implications in terms that made clear this was not science fiction, but a realistic military threat requiring urgent attention. Roosevelt grasped the essential point immediately and authorized formation of the Advisory Committee on Uranium to investigate whether atomic weapons were feasible and to coordinate American research efforts. The committee's initial work proceeded slowly, hampered by limited funding, bureaucratic obstacles, and skepticism from military officials who questioned whether theoretical physics research represented a wise investment of scarce resources when conventional weapons development had proven track records. The pace of American atomic research accelerated dramatically after December 1941, when Japanese attacks on Pearl Harbor and German declarations of war brought the United States fully into World War II. The theoretical possibility of atomic weapons suddenly became an urgent military priority that demanded massive investment regardless of cost or uncertainty about success. In June 1942, the United States Army Corps of Engineers assumed responsibility for what had been renamed the Manhattan Engineer District, or more commonly, the Manhattan Project, under the command of Colonel, later Brigadier General, Leslie Groves. Groves was an engineering officer with a proven record managing massive construction projects, most notably the Pentagon building that was nearing completion when he received his new assignment. Groves brought to the Manhattan Project exactly the qualities needed to transform theoretical physics research into functioning weapons on a compressed timeline that seemed impossible to anyone who understood the scientific and engineering challenges involved. He was relentlessly focused on results rather than scientific elegance, willing to commit enormous resources to multiple parallel approaches rather than choosing a single path that might prove unworkable, and completely unconcerned with conventional bureaucratic procedures when they interfered with progress. Groves understood that the project would succeed or fail based on solving three interconnected challenges: obtaining sufficient quantities of fissionable material, designing weapons that would actually function, and doing all of this before Germany potentially developed atomic weapons and used them to win the war. The fissionable material problem was staggeringly difficult because naturally occurring uranium consisted primarily of uranium-238, which would not sustain a chain reaction with only 0.7% uranium-235, which would. Separating uranium-235 from uranium-238 required exploiting the tiny mass difference between these isotopes that were chemically identical, a task that no existing technology could accomplish at industrial scale. Multiple separation methods were pursued simultaneously because nobody knew which, if any, would work. Electromagnetic separation, using enormous magnets called calutrons, was developed at Oak Ridge, Tennessee. Gaseous diffusion forcing uranium hexafluoride gas through thousands of barriers with microscopic pores was built at a massive facility also at Oak Ridge. Thermal diffusion using temperature gradients was attempted as a supplementary method. Each approach required technological innovations and industrial scale-up beyond anything previously attempted. The alternative to enriching uranium-235 was creating an entirely new element that didn't exist in nature. Theoretical calculations suggested that bombarding uranium-238 with neutrons in a nuclear reactor would occasionally produce uranium-239, which would decay through beta emission first to neptunium-239 and then to plutonium-239, a new element that should be fissionable like uranium-235, but chemically different enough to separate from uranium through conventional chemical processes. This approach required first building a functioning nuclear reactor that could produce plutonium in useful quantities, then developing chemical separation processes for an element that existed only in microscopic quantities and whose chemistry was completely unknown because it had never existed on Earth before human creation. Enrico Fermi, an Italian physicist who had fled fascist Italy and was now working at the University of Chicago, led the effort to create the first controlled nuclear chain reaction. His team built an experimental reactor, designated Chicago Pile 1, beneath the stands of the university's abandoned football stadium, stacking graphite blocks and uranium fuel in a careful lattice designed to slow neutrons to speeds where they would efficiently cause fission in uranium-235. The reactor included cadmium control rods that absorbed neutrons and could be inserted or withdrawn to control the reaction rate. On December 2, 1942, Fermi's team achieved the first self-sustaining nuclear chain reaction in human history, demonstrating that controlled nuclear fission was possible and that reactors could be built to produce plutonium. General Groves selected a remote site near Hanford, Washington, for construction of large-scale plutonium production reactors because the location offered essential requirements: access to the Columbia River's enormous water flow for cooling, isolation from population centers in case of accidents, and sufficient space for the massive industrial facilities required. 3 production reactors would be built at Hanford, each significantly larger than Fermi's experimental pile, along with chemical separation plants where plutonium would be extracted from intensely radioactive spent fuel, using processes developed by chemists working with plutonium quantities so small they could barely be detected by existing instruments. Everything about Hanford operations would be conducted on unprecedented scale, using technologies that existed only in theory when construction began. The weapon design challenge required solving problems that had never been addressed because nothing like atomic bombs had ever been attempted. Scientists understood the basic principle: bring together enough fissionable material fast enough that a chain reaction would develop before the energy released blew the material apart, creating an explosion. But determining exactly how much material was needed, how to configure it, and how to assemble it into critical mass faster than the chain reaction could disassemble itself required calculations and experiments, pushing the boundaries of theoretical physics and engineering. The theoretical work would be centered at a new laboratory built at a remote location where scientists could work without security concerns about German spies or accidental information leaks. Groves selected J. Robert Oppenheimer to lead the weapons design laboratory despite Oppenheimer having no administrative experience, no engineering background, and a history of left-wing political associations that made security officers deeply uncomfortable. But Oppenheimer possessed the theoretical physics expertise needed to understand the weapons design challenges, the intellectual breadth to coordinate research across multiple disciplines, and the charisma to attract the best scientific minds to work on the project, despite the isolation and secrecy that would be required. Oppenheimer selected Los Alamos, New Mexico, as the laboratory site, a remote mesa 40 miles northwest of Santa Fe that offered isolation, defendable terrain, and spectacular scenery that might compensate somewhat for the hardships of living in a secret city that officially didn't exist. Construction at Los Alamos began in late 1942, transforming a small boys' school into a laboratory city that would eventually house thousands of scientists, engineers, technicians, and support personnel, along with their families. The scientists who gathered at Los Alamos represented an extraordinary concentration of intellectual talent, including numerous future Nobel Prize winners, the best theoretical and experimental physicists of their generation, brilliant young researchers who would later become famous, and a few whose work would remain classified for decades. They came from universities across America and from refugee communities escaping fascism in Europe, united by understanding that they were racing against German scientists who had a head start and who might develop atomic weapons first. The initial weapon design concepts divided into two approaches based on the fissionable materials available and their properties. Uranium-235, being chemically identical to uranium-238, could be enriched but not to complete purity with available technology. The gun-type design would fire one subcritical piece of uranium-235 down a gun barrel into another subcritical piece, creating a critical mass that would explode. This design was relatively simple, and the Los Alamos physicists were confident it would work without testing, provided sufficient highly enriched uranium could be obtained from Oak Ridge. The gun design was designated Little Boy and was intended to use uranium-235 as soon as enrichment facilities could produce enough material. Plutonium-239 presented different challenges because it spontaneously fissioned at higher rates than uranium-235, meaning that a gun-type design would begin chain reacting before the pieces fully assembled, resulting in a fizzle rather than a full explosion. The plutonium weapon required an implosion design where conventional explosives surrounding a subcritical sphere of plutonium would compress the material to such high density that it became supercritical and exploded before spontaneous fission could cause premature detonation. Implosion required solving extraordinarily difficult problems about how to create perfectly symmetrical compression using explosives, how to design explosive lenses that would shape detonation waves, and how to achieve compression faster than any previous explosives work had accomplished. The implosion research at Los Alamos was led by Seth Nettermeyer, who had proposed the concept, but the work soon stalled as the technical challenges proved more difficult than initially expected. Groves brought in George Kistiakowsky, an explosives expert from Harvard, to lead the implosion program and drive it forward with the urgency the timeline demanded. Kistiakowsky's team conducted thousands of experiments, testing explosive configurations, measuring compression uniformity, and developing the precision manufacturing techniques needed to create explosive lenses with tolerances measured in thousandths of an inch. The work required innovations in explosives chemistry, hydrodynamics, precision machining, and diagnostic instrumentation, essentially creating entire new fields of explosive science in a matter of months. The theoretical calculations guiding weapons design were led by Hans Bethe, a German refugee physicist who'd become one of the world's leading experts in theoretical nuclear physics before fleeing Nazi Germany. Beth organized the theoretical division at Los Alamos into groups focusing on different aspects of weapons physics, how neutrons behaved in fissioning material, how energy released would affect the chain reaction's development, how much material was needed for criticality under various conditions, how implosion would compress plutonium, and what densities could be achieved. The calculations were performed laboriously by hand and with primitive mechanical calculators, because electronic computers didn't exist yet, requiring teams of mathematicians, often women recruited from universities, to compute solutions to complex differential equations through sheer mathematical labor. Richard Feynman, a young theorist who would later become one of the most famous physicists of his generation, organized computational work at Los Alamos and developed efficient methods for organizing human computers to solve complex problems faster than traditional approaches allowed. Feynman also became notorious for his recreational safecracking and security testing, regularly demonstrating that Los Alamos security measures intended to prevent information leaks were often ineffective against someone with sufficient cleverness and motivation. His escapades infuriated security officers while amusing fellow scientists who appreciated Feynman's irreverent attitude toward military authority and bureaucratic procedures. Security at Los Alamos and other Manhattan Project sites was extraordinarily tight, given the project's immense strategic importance and the absolute necessity of preventing information from reaching German or Soviet intelligence services. Scientists chafed under restrictions that prevented them from discussing their work with colleagues at other institutions, that required censorship of all mail leaving the facility. And that meant they couldn't tell their families anything about what they were doing. The isolation was psychological as well as physical, creating a strange community of brilliant people working on one of the most important scientific projects in history, while cut off from the normal academic community that gave their professional lives meaning. The Soviet Union had begun obtaining information about the Manhattan Project through espionage networks that penetrated various project sites remarkably early in the program's development. Klaus Fuchs, a German refugee physicist working in the British atomic program who was assigned to Los Alamos in 1944, was providing detailed technical information to Soviet intelligence throughout his time at the laboratory. David Greenglass, an army machinist at Los Alamos, was recruited by Soviet intelligence through his brother-in-law Julius Rosenberg and provided additional information about implosion lens designs and other technical details. Theodore Hall, a young physicist at Los Alamos, voluntarily approached Soviet intelligence and provided information about the plutonium implosion design. The extent of Soviet penetration wouldn't be discovered until after the war, and the information provided to Stalin's government would significantly accelerate Soviet atomic weapons development. By early 1945, the Manhattan Project was approaching the point where weapons could potentially be assembled if sufficient fissionable material became available. The gun-type uranium weapon required approximately 64 kilograms of highly enriched uranium, and Oak Ridge enrichment facilities were slowly producing material that would eventually reach this threshold. The implosion plutonium design required only about 6 kilograms of plutonium, because the implosion would achieve much higher densities than the gun design. But the Hanford reactors needed to operate for months to produce even this relatively small amount. Both weapon designs were being refined continuously as new experimental data became available, and as calculations revealed problems or opportunities for improvement. Germany's surrender in May 1945 removed the original justification for the Manhattan Project, eliminating the threat of German atomic weapons that had motivated the initial crash program. Some scientists, particularly among those who had been refugees from fascism, questioned whether continuing weapons development was appropriate now that Germany was defeated. But project leaders, including Groves and Oppenheimer, argued that completing the weapons was necessary to end the war with Japan without a costly invasion, to demonstrate to the world what atomic weapons could do, and to ensure that the enormous investment of resources and effort in the Manhattan Project produced tangible results rather than being abandoned incomplete. The decision to continue was made at the highest levels of government with minimal input from the scientists who had created the technology. The implosion weapon design, now designated Fat Man, required testing before use in combat because the implosion physics was so complex and uncertain that the Los Alamos physicists could not guarantee it would function without experimental validation. A test was scheduled for July 16, 1945, at a remote site in New Mexico called Trinity, where a 100-foot steel tower would support the weapon so that instruments could measure the explosion's characteristics and verify that the design functioned as calculated. The test preparations occupied Los Alamos during late spring and early summer, as components were assembled, tested, and transported to Trinity site. The plutonium core arrived at Los Alamos from Hanford in early July, and final assembly of the test device began immediately. Oppenheimer and his senior staff worked essentially around the clock during the final days before the test, assembling the weapon, installing it on the tower, preparing diagnostic instruments, and dealing with countless last-minute problems and concerns. Enrico Fermi reportedly took bets on whether the explosion would ignite the atmosphere and destroy all life on Earth, a scenario that theoretical calculations had determined was impossible, but that still generated nervous jokes among scientists who understood they were about to release energies that had never been produced by human activity. The tension was extraordinary, as scientists who had worked for years on theoretical calculations and laboratory experiments prepared to discover whether their work would translate into a functioning weapon or fail in some unpredicted way. The weather on July 16th was poor, with rain and lightning threatening to postpone the test, but conditions improved enough that Groves authorized proceeding with the shot scheduled for 5:30 a.m. Observers gathered at bunkers located at varying distances from ground zero, with instructions to lie flat on the ground, facing away from the explosion, and to observe only through heavily filtered goggles or through welding glass. At precisely 5:29:45 a.m., the electrical circuits fired, detonating the conventional explosives surrounding the plutonium core and initiating the implosion that would either create humanity's first nuclear explosion or fail in expensive embarrassment that would waste years of work and billions of dollars of investment. The explosion exceeded even optimistic predictions about its power. A brilliant flash lit the pre-dawn darkness brighter than the midday sun, visible from 200 miles away, and creating shadows that some observers described as sharp as those cast by sunlight, despite the flash lasting only a fraction of a second. The intense heat created a fireball that rose and expanded, becoming the iconic mushroom cloud that would forever symbolize nuclear weapons. The blast wave arrived at observation bunkers with a sharp report that knocked down some observers, despite their distance from ground zero. The steel tower vaporized completely, leaving a crater where the tower footings had been. The desert sand within a half-mile radius melted from the heat into a green glassy substance that would later be called trinitite. Oppenheimer would later recall watching the explosion and thinking of a line from Hindu scripture: Now I am become death, the destroyer of worlds, capturing the terrible realization that they had created a weapon unlike anything in human history. Kenneth Bainbridge, the test director, expressed a simpler and more direct reaction when he told Oppenheimer immediately after the explosion, "Now we are all sons of bitches," acknowledging the moral burden of creating such devastating destructive power. The scientists celebrated the technical success while beginning to grapple with the implications of what they had built and what it would mean for humanity going forward. The Trinity test confirmed that the implosion design worked and that atomic weapons could produce explosive yields measured in thousands of tons of TNT equivalent, the test device having yielded approximately 22 kilotons according to instrument measurements and analysis of the destruction. This success meant that the plutonium weapon could be used in combat as soon as sufficient plutonium became available from Hanford to assemble a second device after the Trinity test device consumed the first core. The uranium gun weapon did not require testing because the physics was straightforward, and the Los Alamos physicists were confident it would function, provided Oak Ridge could supply sufficiently enriched uranium. President Harry Truman, who had become president after Franklin Roosevelt's death in April 1945, received news of the Trinity test while attending the Potsdam Conference with Stalin and Churchill to negotiate post-war arrangements. The test's success gave Truman confidence that he possessed a weapon that could potentially end the war with Japan without the massive casualties that an invasion would inflict on both American forces and Japanese civilians. The decision to use atomic weapons against Japan was made during late July with minimal debate at senior levels, reflecting broad consensus that anything that might shorten the war and save American lives was justified regardless of the consequences for Japanese cities targeted by the attacks. 2 atomic bombs were prepared for combat use against Japan during late July and early August 1945. The uranium gun weapon Little Boy contained approximately 64 kilograms of uranium, enriched to about 80% uranium-235, assembled using essentially all the highly enriched uranium that Oak Ridge had produced since beginning operations. The plutonium implosion weapon Fat Man contained approximately 6 kilograms of plutonium-239, produced at Hanford and surrounded by carefully designed explosive lenses that would compress the plutonium core to supercritical density. Both weapons were transported to Tinian Island in the Mariana Islands, where the 509th Composite Group had been training for the atomic bombing missions using specially modified B-29 Superfortress bombers capable of carrying the heavy weapons. The first atomic weapon used in combat was Little Boy, delivered against Hiroshima on August 6, 1945, by the B-29 Enola Gay, commanded by Colonel Paul Tibbets. The weapon detonated approximately 1,900 feet above the city at 8:15 a.m. local time, creating a blast wave and thermal pulse that destroyed approximately 5 square miles of the urban area and killed an estimated 70,000 to 80,000 people immediately, with tens of thousands more dying from radiation exposure and injuries over the following weeks and months. The devastation exceeded anything that conventional bombing had achieved. A single aircraft delivering destructive power equivalent to what would have required hundreds of bombers carrying thousands of tons of conventional explosives. The second atomic weapon, Fat Man, was delivered against Nagasaki on August 9, 1945, after the primary target of Kokura was obscured by clouds and smoke. The plutonium implosion weapon detonated approximately 1,650 feet above the Urakami Valley, slightly northwest of the city center at 11:02 a.m. local time. Hills surrounding the valley confined much of the blast's effects, limiting the destruction to approximately 2.6 square miles and reducing casualties to approximately 40,000 killed immediately, with additional tens of thousands dying later. The weapons yield was approximately 21 kilotons, similar to the Trinity test and significantly more powerful than the Hiroshima bomb's approximately 15 kiloton yield. Japan's surrender on August 15, 1945, came after the two atomic bombings, and after Soviet declaration of war on August 8, created a two-front crisis that Japan's government could not address given the complete destruction of Japanese military power. Whether the atomic bombings were decisive in producing surrender, or whether Japan would have surrendered anyway due to conventional bombing's devastation and Soviet entry into the war, remains hotly debated among historians. The immediate post-war consensus held that atomic weapons ended the war and saved hundreds of thousands of American lives that would have been lost in an invasion, a view that justified the Manhattan Project's enormous costs and the casualties inflicted on Hiroshima and Nagasaki. The scientists who had created atomic weapons faced profound moral reckonings after the war, as the full extent of destruction at Hiroshima and Nagasaki became apparent. Some, particularly Leo Szilard, who had initiated the entire atomic weapons program with his warnings about German research, argued that demonstrating the weapons on an uninhabited target would have been sufficient to convince Japan to surrender without killing civilians. Others defended using the weapons against cities as justified by the necessity of ending the war quickly. Oppenheimer expressed increasing ambivalence about his role in weapons development, later becoming an advocate for international control of atomic energy and opposing development of even more powerful thermonuclear weapons. The Soviet Union's atomic weapons program accelerated dramatically after Hiroshima and Nagasaki demonstrated the weapon's devastating effectiveness and strategic importance. Stalin ordered maximum priority for Soviet atomic bomb development, directing enormous resources to the program led by Igor Kurchatov. Soviet intelligence information obtained from Manhattan Project spies provided critical technical details that accelerated Soviet progress, allowing them to avoid some of the false starts and dead ends that had consumed time and resources during American weapons development. The first Soviet atomic weapon test occurred on August 29, 1949, much sooner than American intelligence had predicted, immediately ending the American atomic monopoly and beginning the nuclear arms race that would define the Cold War. The Manhattan Project's legacy extended far beyond the immediate military applications that had justified its creation. The project demonstrated that massive government-funded scientific research could achieve objectives that would be impossible for private industry or academic institutions operating independently. The success validated the model of large-scale government science funding that would continue through the Cold War and beyond, supporting particle physics research, space exploration, medical research, and countless other fields. The organizational structures developed during the Manhattan Project, combining academic researchers, industrial partners, and military coordination under unified leadership, became templates for subsequent large-scale technical programs. The scientific knowledge generated during Manhattan Project research established entirely new fields of physics, chemistry, metallurgy, and engineering. Nuclear physics advanced from primitive understanding of fission to detailed knowledge of how chain reactions developed, how neutrons behaved in various materials, and how to control nuclear reactions for both weapons and power generation. Material science advanced through work on plutonium metallurgy, uranium chemistry, and the behavior of materials under extreme conditions of temperature, pressure, and radiation. Computation developed through the necessity of solving complex equations that couldn't be addressed through traditional analytical methods. Electronic engineering advanced through instrumentation development for measuring nuclear reactions and explosion characteristics. The scientists who had worked on the Manhattan Project became influential voices in post-war debates about atomic energy control, weapons proliferation, and the role of scientists in society. Many advocated for international control of atomic technology, arguing that national possession of atomic weapons made war between major powers potentially suicidal, and that only through international cooperation could the weapons dangers be managed. Others argued that American nuclear superiority should be maintained through continued weapons development, and that sharing atomic secrets with other nations would be dangerous. These debates shaped early Cold War policy about nuclear weapons, though efforts to establish international control ultimately failed due to mutual distrust between the United States and Soviet Union. The Atomic Energy Commission, established in 1946 to manage American atomic energy programs, took over facilities and responsibilities from the Manhattan Project's military administration. The transition from wartime crash program to permanent government agency reflected recognition that atomic energy would remain strategically important indefinitely and required dedicated civilian management rather than military control. The AEC would oversee weapons development, nuclear power research, basic science research using nuclear techniques, and attempts to manage the health and environmental consequences of atomic energy production. The health effects of radiation exposure became increasingly apparent during late 1945 and 1946 as Hiroshima and Nagasaki survivors developed radiation sickness and as long-term effects including cancer became evident. Manhattan Project workers who had been exposed to radiation during weapons production, particularly at Hanford and Los Alamos, also began showing health effects that raised questions about safety standards that had been developed based on incomplete understanding of radiation's biological effects. The recognition that radiation caused serious health problems, even at exposure levels previously considered safe, led to extensive epidemiological research and progressive tightening of radiation safety standards over subsequent decades. The environmental contamination from Manhattan Project operations would eventually be recognized as one of the project's most serious negative legacies. Hanford's operations had released significant radioactive contamination into the Columbia River and surrounding environment through both deliberate discharges and accidental releases. Oak Ridge facilities had contaminated local waterways with radioactive materials and toxic chemicals used in uranium processing. Los Alamos and Trinity site had scattered plutonium and fission products across areas that would remain contaminated indefinitely, given plutonium's extraordinarily long half-life. Cleanup of Manhattan Project sites would eventually cost tens of billions of dollars and would remain incomplete decades after the project ended. The moral questions raised by atomic weapons development and use have never been fully resolved and continue generating intense debate more than 7 decades after Hiroshima and Nagasaki. Were the scientists who created atomic weapons morally responsible for how the weapons were used? Should atomic weapons have been used against cities without warning or demonstration? Did ending the war justify the casualties inflicted? Would demonstrating the weapons without using them against cities have been sufficient to achieve surrender? These questions admit no simple answers and remain contested by historians, ethicists, and survivors who lived through the events. The scientists themselves held divergent views about their moral responsibility for atomic weapons and their use. Some, like Edward Teller, who would later lead hydrogen bomb development, expressed no regrets and argued that scientists' responsibility was to create knowledge and technology while decisions about use properly belonged to political leaders. Others, like Joseph Rotblat, who left the Manhattan Project after Germany's defeat removed the threat of German atomic weapons, argued that scientists bore moral responsibility for the consequences of their work and should have opposed using atomic weapons against cities. Most fell somewhere between these extremes, expressing pride in the technical achievements while feeling some degree of guilt or ambivalence about the destruction their work enabled. Oppenheimer's post-war trajectory illustrated the complexities many Manhattan Project scientists faced. He became a public figure, advocating for international control of atomic energy while continuing to advise the government on nuclear policy. His opposition to hydrogen bomb development in the late 1940s and early 1950s, based partly on moral concerns about creating even more destructive weapons, led to his security clearance being revoked in 1954 in a hearing that revealed how political considerations and personal animosities could override scientific judgment in nuclear policy decisions. Oppenheimer's fall from influence demonstrated the dangers scientists faced when their advice conflicted with political preferences or when their past associations became politically inconvenient. The Manhattan Project's success in developing atomic weapons during a compressed timeline that seemed impossible when the project began remains one of the most remarkable technical and organizational achievements in human history. Converting theoretical physics discoveries made in late 1938 into functioning weapons deployed in combat by August 1945 required solving unprecedented scientific problems, developing entirely new industrial processes, creating new materials and technologies, and coordinating work across dozens of sites involving hundreds of thousands of people while maintaining secrecy that prevented even most workers from knowing what they were building. The achievement demonstrated what could be accomplished through massive resource commitment, brilliant scientific and engineering talent, and ruthless focus on results without regard for conventional limitations. But the success came at terrible costs that extended beyond the monetary expenses and included the deaths of hundreds of thousands of Japanese civilians, the beginning of a nuclear arms race that would threaten human civilization throughout the Cold War and beyond, and the burden of moral responsibility carried by those who created the weapons. The scientists who gathered at Los Alamos in 1943 to solve theoretical problems in nuclear physics could not have fully anticipated where their work would lead or how profoundly atomic weapons would shape subsequent history. They created a technology that gave humanity the power to destroy itself, and whether that creation represents tragic mistake or necessary response to threats posed by totalitarian regimes remains debated by each generation confronting nuclear weapons' continued existence. The telegram that Otto Hahn sent to Lisa Meitner in December 1938, reporting impossible experimental results, set in motion a chain of events that would transform physics, demonstrate the practical applications of Einstein's theories about mass energy equivalence, create weapons of unprecedented destructive power, end World War II, initiate the Cold War nuclear arms race, and establish patterns of government-funded scientific research that continue shaping science today. The discovery of uranium fission was pure science, pursued out of curiosity about nature's fundamental properties with no thought of practical applications. The conversion of that discovery into functioning weapons required applied science and engineering at scales never before attempted. The consequences of success continue affecting global politics, military strategy, energy policy, and human understanding of our place in a universe where we possess the power to destroy ourselves.